All right, hey everyone, welcome to week 30 of Chill Kernel Hacking for Fun. This week is going to be pretty exciting. We are finally doing system calls. So in the last couple of weeks, we've been getting closer and closer to this by adding support for interrupts and exceptions and stuff like that. And now we're finally here with system calls. So let's just get going. I'm just going to do a quick test in the chat though, just to see if that's working. See if my Twitter thread worked also, just quickly. All right. So system calls. We're on exercise 7 of lab 3, the MIT class. First, side quest. What's up? Exercise 7. Add a handler in the kernel for interrupt vector syscall. Edit these things. Change trap dispatch to handle the system call interrupt by calling syscall with the appropriate arguments, and arranging for the return value to be passed back to the user process in EAX. Finally, you need to implement syscall in current/syscall.c. Make sure syscall returns e-inval if the system call number is invalid. Read and understand lib/syscall.c, especially the inline assembly, in order to confirm your understanding of the system call interface. Handle all syscalls listed by invoking the corresponding kernel function for each call. Run this program, sprint hello world, and then cause a page fault in user mode. Yo, Calfware, what is up? If this has not happened, it probably means your system call handler isn't quite right. You should be able to get make grade to succeed. Cool. Yo, hey, root vig, educational qualifications for this job role. So to be clear, I don't work in kernel development. This is just for fun, but I have a degree in computer engineering. Thanks for asking. I'm just going to read a little bit of this prior context. Okay. User processes ask the kernel to do things via system calls. When that happens, it enters kernel mode. It saves the process's state. The kernel executes code and then resumes the process. Int instruction for interrupts. Int hex 30 for some reason. 30 cannot be generated by hardware. So there's no ambiguity caused by allowing user code to generate it. The application will pass the system call number and the system call arguments and registers. This way the kernel won't need to grub around the user environment stack or instruction stream. System call number will go in EAX, and the arguments, up to 5 of them, go in EDX, ECX, EBX, EDI, ESI. Okay. The kernel passes the return value back in EAX. The assembly code to invoke a system call has been written for you in syscall. You should read through it and make sure you understand what is going on. Okay. Sounds pretty straightforward. Is your job in Switzerland? I thought you were a music developer. Yeah, I work on synthesizers and music technology and stuff like that. Yeah. Okay. So let's just get to it. So just also recap. So last time I was doing support for some basic interrupts, different kinds of interrupts, for example, breakpoint interrupt. And what is currently happening now is an interrupt can happen, and it eventually makes its way to the C trap function for kind of handling the interrupts in C code. And basically, we dispatch based off of the interrupt number and invoke these just C functions. Yeah, and in this case, handle breakpoint just triggers the kernel monitor, just this thing. So let's, there we go, okay. Also just checking the audio level. So it seems like the music is not working. Is that right? Can someone in the chat let me know if you hear music? Usually I have like some hip hop music playing, but it seems like it's not working right now. Now it's coming through my mic, but it's not being recorded. Technical issues today. Oh well. I'll just try this. I'll just usually don't listen to the music as I code, but let's just try this. Okay, so add a handler for interrupts. So I'll also just clean up a few of these things I don't need. So handle. So now we're doing a hex 30, which is now officially in the reserved territory, or well, no, it's 48 hex. It's hex 30, but number 48 for user-defined interrupts. So I'm just going to do handle system call syscall. Hey, Shovik. Yeah. My question now is, which macro do I use? Because there's one for things that push error codes, and yeah, others, like another macro if there's no error code pushed. And I think there's going to be no error code pushed for a system call. I think the error code is only for kind of specific. Oh, okay, so we can even reference that right here. I'm also kind of curious if we can find that in the Intel manual documentation. Right, so this is the authoritative reference for all this stuff. But I am, so for our syscall, we're not using any of these predefined interrupts. Ah, here we go, perfect. So we're using interrupt 48, and the exception code is not applicable. Good. Okay, cool. not that many low-level channels use VS Code. Well, they should, because VS Code is a great text editor, straight up. Yeah, I'm a fan. Okay, so now I need to do all my typical boilerplate, which is a little bit cumbersome. Okay. No system call. Do I know any that do? No. I mean, I don't know too many other low-level channels. Okay, and then in the IDT. Yeah, VS Code gang makes some noise. That's straight up trap init. So what I'm doing is basically doing the boilerplate for handling an interrupt, which involves a couple different things. So it involves the macro in the assembly for creating an assembly stub to kind of receive the interrupt or get called by the CPU when the interrupt happens. So that's number one. Number two is I need to create a C prototype because we're going to need to reference that assembly stub from our C code, and we need a prototype to do that. And lastly, we need an IDT entry. Oh, what happened? Oh man, this call. What happened? Oh, what? Sheesh. Okay, wow, why did it just delete everything? I just wanted to delete this word. Okay. Does this work? I'm still kind of trying to be a bit better Vim programmer. Somehow my handle page fault thing got erased. It's kind of annoying. No page fault. Okay, and this is actually accessible from user space, so that should be a 3. So now we're set up for ultra basic handling of the system call interrupt. That's actually all we need to do. We can go here. Give me 1 sec to check OBS. Cool. Okay. I just figured out a way to get the chat in the OBS window so I can just stay looking at the OBS window. Yeah. So yeah. It's how long have you been doing C? Yo, what's up? It's Ruda. I've been doing C, I mean, for like 10 years or so, probably. But never really a lot of serious C development. I wouldn't really say I'm that much of an expert at it. But yeah, okay, so now when the system call interrupt happens, it's going to trigger some assembly, which doesn't need to be changed, and then it jumps into the C code, and it's going to hit the trap dispatch. And for the moment, it's not going to hit any of these switch statements. It's going to hit the generic handler, basically. And I kind of just want to see that happen, just for starters. Quickly just checking what our working tree looks like. So this is the diff. So it's just those 3 things I was talking about: the macro for the assembly stub, the IDT entry, and the function prototype. And I think there's probably better ways to software engineer this to make it not so much boilerplate, but I'm not so interested in doing all that software engineering stuff right now. Okay, so I'm just gonna run it. Let's do run hello. And my guess at what's gonna happen, maybe I'll just show hello.c. Hello.c is a simple program that does a hello world. And it's going to make a syscall in C printf when it, maybe we can even browse. I'm actually not so familiar with this part. At some point it's going to make a system call, I think. Print num, put char. Ah, it's a function pointer. Okay, that's interesting. But it's put char. Okay, it's very hard to follow this control flow with the function pointers everywhere. Okay, whatever. I'm just going to run it, and my expectation is we're going to see something a little bit like this, but it's going to say, it should say hex 30 in this trap thing. Let's try. It actually did a page fault, which is actually kind of unexpected. Interesting. Okay, 20-minute break timer to stand up and stretch. Be right back. Okay. So that is interesting. I am going to debug this, I guess. Hello. Oh, I see. I think you're right, SideQuest. I think I was a bit sloppy. Wait. I think trap.c. Yeah, it might have been in my IDT. There, yeah, you're totally right. Yeah, so that's a strong reason why you're totally right. Good catch, SideQuest. Thanks for paying attention. So that's an example of why it might be good to invest in that software engineering work that I wasn't doing. Awesome. Yeah, you were totally right. No, yeah, hex 30 system call. So that's exactly what I was hoping would happen. Nice. So what next? So that is at least initially working. So now we can go to this patch and dispatch on syscall. And is there a syscall handler already, or do I need to make one? By calling syscall in syscall.c, I see. Okay. Wow, I just highlighted. What happened here? Why is it all highlighted? Ref.c. Okay. Syscall.c. So here we are at the main C syscall handler. So I'm going to do syscall. Okay, but no, I'm not going to directly call it. It requires some special arguments and stuff, so I'm I'm just going to do a handle syscall in the same way I have all these, like the handle breakpoint and stuff. I think I need to do some some assembly here to get the arguments to pass actually. Call the function corresponding to this call. Right. What does it say about this? You need to change trap to handle the system call by calling syscall with the appropriate arguments, and then arranging for the return value to be passed back. Okay, it doesn't actually give much information about how to do this, but we're going to need to access these registers, I think. So that will be exciting. I don't actually really know how to do that actually. We'll need to figure it out. We will definitely need some assembly. I'm not sure if inline assembly will be the best option or an actual separate assembly file, or if maybe that's already provided. So basically call syscall is what we want to do, and in order to do that we need to have all these things. It is our part of the trap frame. Actually, yeah, I think you're right. I think you're right. It's that request. That's a good point. Yeah. Yeah, because what happens is when the interrupt happens, it triggers our trap entry.s, which runs this code, and crucially, we have this push AL, which pushes like all the registers and constructs the trap frame. So yeah, very, very sharp observation. So this is actually going to be pretty easy since all that stuff is just there. It's going to be trap frame dot, is it registers dot EAX. And then basically we just need to, do I have I don't really have auto formatting here unfortunately yet, so I'm just going to do something like this and figure out the formatting later. So first thing is the syscall number, and then we have all these arguments which are listed right here. So I'm just going to if I was like really clever, I could probably use like multiple cursors somehow to do this. How do I do this? Something like that. Is that even right? So yeah. So EAX, then EDX, ECX, EBX, EDI, ESI. Nice. Gotta go. All right, nice. Thanks for joining SideQuest. I'll see you next time. Thanks for the help. Okay. So that means we're actually going to start calling this C code now. Called function corresponding to the syscall no. So now I'm just going to run this. I'm expecting that we're going to hit this panic syscall not implemented. Yo, Pengu XOR, what's up? It's going great. It's going absolutely amazing. This syscall support is going pretty well so far. We're now handling the syscall interrupt and panicking at the syscall function. So, yeah. Yeah, my streaming setup is a bit messed up today. Like for some reason it's not capturing my system audio, so it's just my mic today. Okay. And arranging for the return value to be passed back to the user process in EAX. Okay, let me just do that part also. I didn't quite handle syscall. Actually, I think something like this. It's like a little bit noisy. I'm gonna make maybe just add a variable. It's an int. It's a signed int. That's kind of weird. 2t. Right. X is ret. Okay. All right, so now finally implement syscall in kernel syscall.c. Make sure syscall returns e-inval if the system call number is invalid. It seems to do that already. All right, well, I don't exactly know what I need to do here, but I do know that I need to return value, so I'll just get that out of the way. And now I need to dispatch based off of the system call number and invoke one of these system calls. I wonder if we can get some more information in syscall.h. No. Syscall.h in the include. Here we go. Yeah, so here's where all the system call numbers get declared. And C puts break. C puts. So now it takes 2 arguments, and I'll Okay, so just for a little bit of a start, it's going to be A1 and A2. And that's going to produce compiler warning because of the types. Okay, it's not, at least I thought it would, because now we're casting from an uint32t into a char star. Yeah. Yeah, so I the easiest thing to do is just cast it to a the type const char at s t, which is a little bit annoying, kind of, but this should at least compile again. I have a syntax error. Do I? No, wait, what? What are you talking about? Oh, wait, what? Oh, yeah. That's why. Okay. Void value not... Oh, what? It doesn't return anything? Okay, so maybe it's... Is it e-success or something? Or what do I return actually? These are all the actual errors, but what does it say about that? If it's live print from it.c. So these actually, yeah, these go up. I think I just returned 0 or something like that. Right. I'm just going to do that for now. So now we have this. Okay, oh yeah, and it's assigned int because, yeah, because the convention is to return a negative integer for error codes. Nice. Yeah, I guess I will just do these other ones then. Scall h. I'm just going to do 2 of them. I'm just going to do these first two. C get C. Which is just void. But I'm not even sure I need this one actually. Just for the sake of the hello world, I don't think I need it. So what does it say though? Make sure it returns eval if the number is invalid. That already happened. Okay, understand this thing to confirm your understanding. Okay, let's just do that quick. Syscall.c. So this is the user space code in like the libc that ultimately triggers a syscall from user space, given some parameters and I guess some other stuff. Oh, wow. interesting. So yeah, this is kind of interesting inline assembly. I guess the A is short for EAX or something like that. It's like EAX, then EDX, ECX, BX, and D and S is capital. Some kind of GCC language for this. Okay. What I actually just want to do is not really read the C code, but just read the assembly, which will be, I think, easier to understand than all of this stuff. Looks like we need to do an obj dump, obj lib, syscall.o. Yo, what's up, Dev Suthar? Hello, hackers. So this is, here we go. Yeah, this is the actual assembly code of the syscall function, and to me, it's a lot easier to read than this thing. So, yeah, we are anonymous. Yeah. Right, so we enter the function, do our function prolog, push some of the Kali saved registers, drop the stack for some reason, and then move a bunch of these arguments into the various registers. Yeah, D, C, B, D, yeah. And then trigger the interrupt. And then we do this branch to check, if the interrupt was, if the return value was 0. All right, 20-second break, be right back. Okay, but anyway, that was just, yeah, so that's relatively straightforward for me. Yo, what's up, Bishwaz? I'm following this MIT course, which I'm going to link you to. So what was going on there? Okay, okay, make. So let's run this hello thing. Oh, okay, I still have the panic there. That's why. So, so here's what's going to happen. It's actually going to like run the system call. It's going to work, I think. So if we go to our hello.c, I'm expecting that this C printf is going to fully work. We're going to see like hello world somewhere on the screen. But I think then it's warning us that this env thing is going to crash. Yo, what's up, gaming with Amit? I will answer that in 1 second. It should print hello world on the console, then cause a page fault in user mode. So, yeah. Yeah, Amit, I am working on this operating system. I'm following this coursework from MIT. And I'm making system calls work today, which allow user space to trigger functionality that's exposed by the kernel, such as printing out strings. All right, let's run it. There we go. Hello world. It worked. Yeah, that's cool. So we successfully entered the kernel, dispatched the interrupt, executed some code, and returned back to user space and kept executing, and then the page faulted, which is exactly what is supposed to happen. Nice. That's pretty satisfying. Okay. So okay, it's saying handle all the syscalls listed in that by invoking the corresponding kernel function. So we can go and do that now. So none of these are actually relevant for this particular task. Syscall h. So there's 2 more syscalls. Oops. Oh, okay, I don't know what the actual, is it out env destroy? Or there's some system call for destroying an environment. Interesting. I guess that's kind of, maybe that's like the exit system call. But, okay. Get env ID, and what are the arguments? It's just void, but it returns something. So what about getC? getC also does it, right? So I need to be careful and try not to be sloppy about that. cputs is void, right? But yeah, getC returns something. Get env ID returns something. Yo, Ismail, what's up? Hope you're doing well. This is a pretty good day for me today. We got system calls going, implementing some system calls. I just don't know what to do with this env destroy thing, because let's see. Puts getC. Oh, it's right here. Okay. It needs an env ID. And it returns something. But this is going to be env destroy. And it builds. Nice, good to hear. So yeah, I'm going to just run it one more time just to see the hello world, which is very satisfying. Hello world, W's in the chat, please. That means we're finally triggering the syscall. So, and I think we're done with the lab. So, exercise 7. Done. Oh, but I need to check the grading script. You should now. Okay. Maybe yeah. Let's see if the grading script works. Okay. Yeah, I had commented a lot of these out. Right. Okay. What's the best Vim way to comment out the entire paragraph? I could, with VS Code, do VAP, and then that, yeah. And then, can I nope. Ugh. Okay, it's annoying. Okay. Then there's all these things, which I should probably run. Let's see. I don't know. And I'm kind of, how do I run the tests again? Make, it was just like grade, yeah. It's a grade lab 3, I think. Moment of truth, test BSS. Oh, shit. Okay. Interesting. Okay, apparently I have some more work to do. Let's take a look. So test BSS, what is test BSS? So test BSS just declares a large array globally and checks that it's 0 initialized and that if you write something to it, now doing a wild write off the end, should have trapped. And let's look at the grading script. Making sure BSS works right. Doing a wild right off the end. User fault. Okay, so now apparently hello is failing. Let's look at What's up, Sork? What are you code? I'm coding in operating system, but only kind of. I'm just following this classwork, but it is an operating system. Yeah. Hello. I am. So apparently, okay, I'm gonna go back here and minimize it to just these. Let's just get hello working. Or wait a second, it says I am environment blah blah blah, but I haven't implemented support for that yet. I'm not. Okay, never mind. You should all wait a sec. You should also now be able to get make grade to succeed on a BSS test, and that's it. Okay, and I have that working, so I think I'm done with exercise 7. So I'm going to go ahead and commit this. Delete that. Nice. All right. Boom. All right, how long does it take to understand coding or in Python or maybe C#? It'll probably take you a few years, to be honest with you. You can learn coding kind of quickly. It depends on what you want to do, but to really get things, you need to practice for a long time. But I mean, you can learn Python in much less than 3 years, though. You can learn some basic Python in like a few weeks, I feel like, if you just follow some tutorials and stuff. So yeah, I think Python is a good place to start. Okay. So here's this challenge, which I actually am extremely curious about. Implement system calls using sysenter and sysexit instead of using int30 and iret. So I would love to understand this better. It's like doing these interrupts for system calls is such like an old school way to do it, and no modern OS uses interrupts. At least for x86, no modern OS uses interrupts. This uses interrupts for system calls. What happens? I guess the music is going. All right. All right, so yeah, what's up with these? So these are these instructions that are designed to be faster than int iret. Use registers instead of the stack and make assumptions about how the segmentation registers are used. Exact details we found in volume 2. Uses a way to add support to add a sysenter handler in kern/trap.s. Some model-specific registers. Wow, some random. Okay. Okay, I'm very interested in doing this, but I think now is not exactly the right moment because I want to keep making just forward progress on the main kind of progression through this course work, and so I'll probably try to come back later and do that. Yeah. So exercise 8, add the required code to the user library. Then boot your kernel. You should see user/hello print hello world, then print I am environment 1000. It attempts to exit by calling env destroy. C libmain with exit to C. Since the kernel currently only supports one user environment, it should report that it has destroyed the only environment, and then drop into the monitor. Make it succeed on the hello test. Okay, so what do I do? You should modify libmain to initialize this global pointer this env to point at this environment's struct env in the envs array. So this is kind of that weird part where user space can actually access all these kernel data structures directly. Note that lib/entry has already defined envs to point at the UMs mapping set up in part A. Hint, look at inc, env.h, and use sys get env.id. Libmain calls main, umain. So Ismail, this is what you asked about last time. The umain thing is just randomly named umain for user space main, I think, or user mode main, which in the case of the help program is this. Okay, time to access UMs. So, should modify libmain to initialize this global pointer, this env. Let's check it out. libmain.c. Set this env to point at our. So it's set to 0, and it's a global pointer. Okay, I see. So we need to And lib entry.s is already defined. Define symbols ems so that they can be used in C as if they were ordinary. Now this is interesting. This is interesting because this is actually a shared header between the kernel and user space, actually, which allows user space code to reference these like symbols and defines that are declared in the kernel, which is kind of neat. So we have these ems array, and just for a recap, here's our memory layout, and ems is this area, which it points to this array of the environments, and an environment is just our data structure, our struct env. It's just our data structure for like a process, basically. And it's stored in this array somewhere, I guess here. And initialized. Where is it initialized again? I was just trying to find all the references to this variable. Okay. I think probably here. Yeah, this is where we initialize it to just some like allocation, but it happens at runtime, which is kind of funny because it's a static. This is just a compile time constant. But anyway, so in our lib main code, what we need to do is basically okay, so env id equals get env id. All right, 20-second break, be right back. Wait, so what did it say again? Inc, right. Inc env.h. What is this? Or, well, what? I mean, I need to just basically index into this array using what I get from sys get env id. The question is just how do I call sys get env id? I don't know if I've get env id. So there's, oh, okay, yeah, so it is exposed to, it is available in the library. So that just means, what does it return again? An env id t. this. Error check this. I think this should work. I'll get to the questions in 1 second. So what do I think is going to happen now that I wrote this code? I think basically this is all the necessary code to make hello.c actually run, because now this part is not going to crash. Trying to access, I mean, it was basically sort of like a null pointer dereference-ish. This env was a null pointer, and then we were accessing some struct member from that, and that was crashing, I'm pretty sure. We can actually just maybe see that quickly. Yo, Chiller, yeah, welcome. I'm writing an operating system following this MIT course. Yeah, which I can link it to you. So I'm just going to remove this really quick, and I believe we should see something that looks kind of like a null pointer dereference. Not exactly, but kind of close to it. What's going on? I think it, wait a sec, what? Okay, I'm a little bit confused actually. I'm not seeing a hello world. I'm also not seeing a crash. What did I change? I did not really change anything. Okay, I don't know what's going on. I don't see a hello world like I thought I would, which we were just seeing. So what happened? I have too many tabs open. I feel like something, man, what could have possibly happened here? This does not make sense. Whatever, let's just maybe debug it really quickly. Oh, shoot. But how do in order to debug it, do I need to go back and change this thing? I might, that's a little bit annoying. So it didn't run. It didn't hit the breakpoint. Which is kind of what I thought. That's so strange. What? I'm going to stash. Yeah, wait, so this worked, right? Yeah, wait, what the? So that actually, so something something that I stashed, like, broke it all. Like, it was just working. Yo, Handle, what's up? Did I not commit? So now I'm back here, and it's just all working. Oh, maybe it was actually something wrong here. Yo, morning coffee and chilling, nice. Sounds like a nice one. It might have actually been this. Okay, let me unstash. I'm just going to I'm gonna pop that stash. Today we're doing system calls. Yeah, so I think it was actually, yeah, we're making pretty good progress on system calls actually. Trying to get basically just running like a hello world program in user space. I think that was it. Let me run this again. Yeah, it's working now. So something happened. Yo, what's up, Yakto Leaf? This is called Lazy Git, the thing on the right. It's pretty good, yeah. Okay, so this is actually working now. So the problem was actually calling this syscalls. Did it crash? Or did I, did I route this wrong? So many embarrassing bugs. Did I accidentally call, or is this still called? No. But I'm actually curious. Actually, we should get here actually. So I'm going to, and this is the coolest thing, because I'm in like, so just to check. So now we're using hello, right? So make move GDB, break syscall. Yeah. So system call number 2 is running right now. So what is system call number 2? Get env ID. It would be awesome if I had a backtrace. Oh, I do have a backtrace. Wow. Without even trying. But it doesn't go into user space. Yeah, it just ends somewhere. It would be nice to know what the user space stack trace is. Am I seriously going into sysenv destroy right now? I am. Why would that be the case? Is it? Oh, that's why. Forgot the break. That's why. Okay, let's run it. Hello world page file. Okay, so now that's working again. Good. Yeah, I have an off-topic question. Elon Musk, you have to work every waking hour. I mean, I think I would not agree that you need to work every waking hour. I think rest is extremely important. So if you're asking my opinion, I mean, yeah, strictly speaking, I wouldn't agree with that. Yeah, I think there's some middle ground to be had where I think his point is just like you need to work hard to achieve hard things, and most people are not willing to work as like hard to his definition of hard. And I would agree you need to work hard to achieve hard things. I also definitely recognize the importance of rest. Otherwise, you'll burn out, and it's physically unhealthy to work every waking hour. Yeah, great question. Okay, let's do this. So now we got the env ID. Just curious, is this a signed type? It is a signed type. So env ID less than 0. I don't know. Panic. Can we even panic? Env ID is less than 0. Invalid. Env ID. Something like that. So this did not work yet. Interesting. Can I see printf here? Env ID 4096. Okay, so it looks like I might have a bug with my virtual memory because this is page faulting. I think this is the address. Okay, something is a little bit odd and ends. Do I have like a case sensitive search on or something? Why is it not? Oh, and okay. One to the 10. One should. What is that? Probably 4096. 1024. So something is whack. So it seems like the env ID is way too high. Let me maybe add another assertion. Or can I actually assert here? Is there a user space assert? There is. I don't completely know if this is right. Oops. Assertion failed. Yeah, okay, so the end ID is way too high. There should only be 1,000 slots for environments. Also, where is this thing declared? Inc. For some reason. Or maybe I'm doing this wrong, actually. Oh, wait, no, I am doing this wrong. Because apparently I didn't know what an env ID actually is. An env ID is not just an index. Okay, this is part of the OS that I really don't understand very well, this whole environment ID stuff. But the index, right? So I need to, so I need to call it env this thing. Let me get lib main over here. Can I just do this? Can I access that macro? Because it's in this inc shared thing, yeah. Okay. Now it works. Okay. Good. So I don't have problems with my virtual memory, I think. I think that, so to explain it in a little bit more detail, so what this is doing, so this is the code that runs like pretty early in user space for every process to set up the user space environment. And one thing it does is set up this global pointer to point at this particular process's like data structure that resides within the kernel. All right, 20-second break. I'll be right back. So yeah, every process in the OS has a data structure associated with it. And the OS actually decides to expose all of these data structures to user space. So a process can actually access like its own structure and apparently like all the other structures, I think, too, because they're all mapped to read-only. Yeah, it's a relief. Yeah, it's always a gamble. I never quite know if it's like a small bug or like my whole code is totally broken. So, yeah. So you can get rid of all this stuff. But yeah, basically something like this. Greater than or equal to 0. Probably less than 1024, I think. Because 1023 is probably the maximum index into there. I mean, I don't really get this stuff still, though. I understand there's this idea where it's like a 32-bit ID. The lowest 10 bits are the index into the environments list. There's some uniquifier. Okay, some kind of like nonce sort of thing, because there's a fixed amount of slots in the environments list, and they can get reused. And so the index is not enough to know like an index alone could have referred to multiple processes that executed within like at different times. And so if you want to uniquely identify a process execution, you use this unifier, this whole thing. Is this a Unix thing? I think this is not a Unix thing. I think this is a weird thing that only this operating system does. I've never really heard of this before. I think this is really a very strange implementation detail of JOS. Yeah, but maybe I'm wrong. I don't actually know that much about this. All real environments are greater than 0. env idt equals 0 is special and stands for the current environment. Interesting. Okay. So basically that worked. Like, that's all there is to it. The hello thing, like, is fully working now. Okay, I kind of, so that was the important bug fix, which I will amend into the previous commit. This is the minimal change to make hello run, and then I'll just remove this thing. This and this and makes hello run. Okay. So you should see it say hello world and then print I am environment blah 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 blah. Hello world, I am environment blah 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 blah. And also over here, oops. There should be a I thought Kimu had some kind of I don't see it. Yeah, like some virtual screen that Kimu makes. I'm just in the console right now. But it says, hello world, I'm environment 1000. So I'm gonna call that done. That's it for exercise 8, I think. So now make grade should succeed on hello test. Or grade lab 3. So now let's run it, grade lab 3. Okay, yeah, so that works. Awesome, good stuff. So now moving right along to page faults and memory protection. I'm just gonna skip that and look at exercise 9. Okay, change this to panic if a page fault happens in kernel mode. To determine whether a fault happened in which mode, check the low bits of the CS. Read usermem assert and implement usermem check. Change syscalls to sanity check system call arguments. Boot your kernel running user/buggy hello. The kernel should not panic. Okay. So basically, this is basically kind of implementing, like, kind of handling if the program does really wild memory accesses and then gracefully killing the process and not crashing the kernel. So this is that thing I was talking about earlier, where it would be really cool to see a backtrace from the kernel that even goes into the user space code. But I don't know if I can do this because I never really got all this stabs stuff working, actually. So, yeah. Okay. Quickly read this context, memory protection. Program accesses invalid data or address with no permissions. The processor stops it and traps into the kernel with info about it. If all is fixable, it can fix it and let the program running. Otherwise, you kill the process. Okay, this is interesting. System calls are an interesting problem because the interface allows you to pass pointers into the kernel. The kernel then dereferences the pointers. Okay, page fault is a lot more serious. While maintaining its own data structures, that's a kernel bug. And the handler should panic the kernel. Okay, so it's kind of making this assumption that the kernel never page faults on its own memory, which is a pretty common assumption. I think at least when Linux works like that. So the Linux kernel virtual memory is not paged out or anything like that. It's always paged in. So this is consistent with that. But the kernel needs to distinguish that if it's trying to access user space memory and a page fault happens, that is okay. But one thing I'm actually a little bit unclear of is the difference between a page fault and a general protection exception. Yeah, like, okay. So basically it's saying, okay, kernel needs to be very careful with the pointers it receives from user space. Okay, that's what it literally says here. Solve these problems with a mechanism that scrutinizes all pointers passed from user space. When a program passes the kernel a pointer, kernel checks the address is in the user part of the address space. Yeah. And the page table would allow the memory operation. Thus, the kernel will never page fault due to dereferencing a user supplied pointer. Okay. Okay, let's try it out. So trap.c, and also let's just Google something. Okay, close all these things. Can I close all? Close all. Okay, so many tabs. Let's clean it up. Trap.c. Okay. Continuing preference CPD. To panic if a page fault happens in kernel mode. Let's see. So we can handle this in here. And we already have this nifty check that checks the low bits. So we can do I'm just kind of sloppily coding it right now. From kernel mode. Okay. So what, this like panics or something? Do panic. But wait a sec. if a page fault happens in kernel mode. Okay, that's okay. So I'm in the wrong place. This is a very general place, but I need to specifically check this in the page fault handler. Right. Okay. Okay, yeah, lab 3 code here. Panic. Maybe received page fault from kernel mode. We've already handled kernel mode exceptions. So if we get here, the page fault happened in user mode. Do I talk to the, does he talk to the chat? I do talk to the chat. You know, what's that, arbiter random user, or arbit random user? If my audio is working, which I hope it is. Yeah. Okay. I kind of wanted to just test this a little bit actually also. Buggy hello. Unmapped pointer passed to kernel. Buggy hello 2. Pointer to region extends into unmapped memory. Okay. Maybe something I can just quickly hack in here to test. So I'm going to mem layout. I'm just going to put in a dereference. Oh, what's it? Kernel hacking for fun. Yeah. Yeah. Yeah, I'm just going to choose this kernel address and try to dereference it, which should, wait a sec. Never mind, that's not going to work. Because this is coming from, wait a sec, what? This is, if a page fault happens in kernel mode, right? Kind of goes back to, I'm like not remembering the detail of exactly when when a page fault is triggered. Like if a page is not present, right? So if a page is not present, proceed, privilege level. So the easiest way to try to do it is find an unmapped memory. I actually don't, but yeah, but this is not going to work because that's coming from user space. So actually, we just need to find like we need to find, to test that this works, we need to find some random C code and just like cause it to crash basically. And I think we can just do that after we've initialized all the traps. So for example, that is a null pointer dereference, and 0 should not be mapped. Empty memory. So this should actually, in theory, cause the panic. Let's check it out. Literally anything will work. Make Kimu. Does this work? That didn't do what I thought it would do. Okay, that. Did not work. For some reason. The page file is not from user space. I'm intentionally trying to trigger a page file that happens from kernel mode in order to hit this panic. But I'm kind of being a noob in that I don't actually know how to make, how do you make page faults happen? That's kind of what I was trying to figure out. Like, it's a topic that's not so fresh in my head. And the way, I think, like, as soon as, like, trying to access some memory that doesn't have a present bit should immediately trigger it. Maybe this is getting optimized out. That would suck. Oh. It's possible that's getting optimized out. Should crash. But maybe if I do this, it won't. Try to print it. Oh, let me try. 20-second break. Be right back. Let me try this one more time. What? What? Yes, okay, that worked. Man, it's like, it's so tricky to tell whether, like, is my understanding completely wrong, or is it just optimizations are not enabled? Who knows? But basically it worked. Received page fault from kernel mode. This is pretty cool because we're finally kind of graduating out of this early phase of OS development where any kind of crash in the kernel causes reboots, like, constantly, which is kind of what I've been dealing with, like, the last, I don't know, 4 months or whatever. And we're now out of that. If the kernel crashes with some kind of seg fault or something like this, it doesn't just reboot the machine a million times anymore. It like hits this panic now. It's basically kind of like our own equivalent of a blue screen of death, except it's just not blue and it just says received page fault from kernel mode. But I think it's like a pretty similar thing. So yeah, that's kind of cool. It would be nice to have some kind of test for this, like some. Yeah. So, some like integration test or something like that. I don't know. I'm just gonna not think about that for right now. So I've done the first part. Now read user mem assert and implement user mem check. I'm not sure it provides test cases for that thing. It does provide a lot of these test cases, but all of these test cases are from running user space code. And so none of them are going to be able to trigger this panic because this requires the crash to be coming from the kernel. And so in order to have a test for that, at least the idea that comes to mind for me is we would need to create kind of like a test system call that just crashes the kernel. And then user space can trigger the crashing system call. And we can assert, like we can check that this panic is received and stuff. Yeah. Yo, hey Sad. Sorry, first video, XP6 gardening. Thank you. Yeah, come a long way since that first video. No longer doing XP6, doing JOS instead, but still very much doing this gardening mentality, I would say. Yeah. Okay, so pmap.c user mem check. But it said read the code, read user mem assert. Does this not exist? Okay. Checks that environment is allowed to access the range of memory with permissions. Perm. If it can, the function returns. If it cannot, env is destroyed, and env is the if env is the current environment, this function will not return. What does that mean? If env is the current environment, this function. I don't quite get what that means though. I don't. If env is. Okay, this code is like a little bit hard to read because it would seem like you call env free, and then you would always just hit this, but that's not the case because I think env free schedules another environment at the end, and therefore it doesn't return or something. I don't actually know. Maybe I'm wrong. Maybe I'm totally wrong. That would be kind of weird actually. I actually don't really see any sign of that. So kind of a mystery to me how this works. It would appear like it would always hit the while one loop. But anyway, more importantly, going back to here. Okay, so if user mem check, so we need to implement this now. Okay, let's do that. Check that an environment is allowed to access the range of memory with permissions. Present. Okay, some more virtual memory programming. Tricky stuff. Okay, that's either 1 divided by page size, 1 divided by page size plus 1. Okay. A user program can access a virtual address if the address is below ulim and the page table gives it permission. These are exactly the tests you should implement here. If there's an error, set this variable to the first erroneous virtual address. Interesting. Returns if it can or e-fault otherwise. Okay. Time for some real kernel hacker coding with virtual memory. I always find it helpful to draw these things out, which I will do here. I mean, we kind of already have some other diagrams. Yeah, I think this is a good diagram. That's pretty helpful. So here is an example section of memory with 3 different pages. We have 2 arbitrary points in here that can be at any kind of like level of alignment here. So we need to round the VA all the way down. We need to round the len. Or do we need to round the len up? Not. We need to definitely. Check the environment is allowed to access the range of memory. Okay, so are we allowed to? So starting from here. Test every page that contains any of that range. That's either len divided by page size. Len divided by page size plus 1. Or len, okay. Len divided by page size, if it's completely aligned, then len divided by page size will be the amount of pages. If it's not aligned, for example, then we might have to add, like, for example, if the len was actually on this thing at the end, this distance is not 2, it's like it's rounded down, like len divided by, so this len divided by page size is going to be, it's like 1 point something something something, so the point something 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 gets dropped off because they're talking about pointer arithmetic here, and then, but we do need to check this page, and it's kind of this thing, I'm not, len and page size plus 2. Oops. So what, how, or maybe this. Okay, so I guess maybe this is like the worst case scenario where, yeah, for example, so if we put these really close, the distance is like 1 point something 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 pages, but we still need to fully check this one on the end and this one on the outside. So that explains all these cases. So now I understand it. So now, and it's saying we should, to the first erroneous virtual address. Okay, so there's more efficient ways to implement this and less efficient ways to implement this. The least efficient way would be to literally iterate over every single address and do the check, which would be kind of stupid. I think what I'm going to do, I'm just going to move this away just for a sec. Yo, what's up, Spider-Man? What the heck is going on? Spider-Man, good name. Okay, so what's the approach here? We need to start here. Okay, we have this range. We need to iterate through every single page of the range. And I'll just kind of start free coding. First VA. So that's just going to be round down VA page size. For I equals 0. Or I guess maybe it's like current. Maybe I'll do it so like this. Or maybe even, yeah. Okay, I'm gonna simplify just a little bit. So basically, we'll get our starting point. We just take VA and round it down. And we are just gonna check every page. So our loop is just going to check if can access cur. And cur equals page size. And when do we stop? If so, cur, right? So cur VA could be aligned, in which case cur is going to be equal to VA, or VA could be unaligned, which means cur needs to be rounded down. Cur is just going to bounce along, and then the end condition is when cur is greater than the final address, right? What if the final address is actually perfectly aligned on a page? That's so if that's the case, we don't do the check. So something like this, roughly sketching out this code. Does this even compile though? I'm doing all this pointer arithmetic. Oh, what? 59. Wait, what? Wait, did I? An expansion. Oh. It's a const void. You're telling me I can't. Initialization discards const qualifier. You're telling me I can't okay, whatever. Const void. Yeah. Okay. Okay, good. So using some const. So we basically got our current. Got our current and our end. And let's just make it a bit spicier. Let's just, yeah, this to make this, man, I can't. To make this as spicy as possible, aka the worst possible edge case, both are going to be unaligned. So the air condition was that cur, if cur is greater than or equal to end adder, we stop. So the opposite. Okay. So while cur is less than end adder, we bump to the next page and check it. And this will happen here. So for example, we'll be bumping along and cur will be less than this line, so we will check it and run the loop. And then we'll bump to the next one, and cur will not be less than this. And then if this thing happens to be perfectly aligned, we'll bump along, and cur will be equal to the env-editor, and that equal is not less than 2, and so we won't run it. And so I think that is a somewhat reasonable for loop. And now we just need to check the access, which we can do with check page. I've kind of forgotten all of these APIs. No, that's totally not it. Oops. Huh. Page lookup? I think it's page lookup. You pass in what? The page dir. So with the env page dir, then what? The VA, which is going to be cur, and then a PTE. We need to declare, we'll just declare it here. And we got the struct page info. Okay, struct page info. Page info. At least I think that's the function I want. There's also these low level ones like pagedir walk and stuff like that. And can be used to verify page permissions for syscall arguments, but should not be used by most callers. Yeah, but that's exactly what I'm doing. Verifying page permissions for system call arguments. And just for a refresher, this one tries to look up the virtual address and returns null if it couldn't find it. And if it could find it and you gave it a pointer, it stores the PTE pointer in there. Okay. It's already 6, but this is too juicy. 20-second break. So I think this is what we want, I think. So now I'm just going to go back here. Okay. Okay. Return 0 or e-fault otherwise. I'm just going to add a go to fail return e-fault. Or not go to, just fail. How do we go to, come on. I kind of forgot how to do that. Yeah, that's how you do it, right? Okay. Is default undefined? any_fault. Okay. So now we're checking each page. Okay. So first test, if, well, technically we don't even need this thing for the first test. It's just like if cur is less than, or what? If it's below, so if cur is greater than equal to ulim, go to fail, something like that. I'm just thinking about this annoying thing where we need to assign this thing to the first erroneous virtual address, but okay, maybe I'll just keep them together at the bottom. So and if page table gives it permission. So what would it look like for the page table to not give it permission? So if page info equals null, I kind of don't exactly know what I'm doing. I'm just kind of sketching out the rough checks. It's like, okay, VA was not in user area. This means that the VA wasn't mapped to physical mem. I kind of need to, I want to have the page lookup right here. Or maybe page dir walk is what I want. It's basically what I want. I don't actually know if I need the extra information returned by page lookup. If this thing, but yeah. So if it wasn't present, returns null. Okay. If it was a null pointer, it returns null. If it actually had something but it wasn't present, so what triggers this case again, where this thing returns null? So here it does the internal check. If it wasn't present, it just returns null. That's pretty much the main time. So it actually kind of, I'm thinking that it doesn't really make sense actually. And this might be redundant. But in any case, so if it was null. I kind of feel like it's helpful to go back just to the diagram real quick. Okay. But I think, so, the page present, or, Then what's the condition? It's something like, yeah, PTE. So we have some permissions we're trying to access it with. Mostly, it's just mostly the read, write, and the user supervisor. Like none of these other things are really permissions. Yeah, Miro is a good tool. I like it. Very nice for mind mapping and diagramming things. Okay. Normally perm will contain PTU at least, but this is not required. So it could be asking for user permissions. I mean, basically, by permissions, we mean like readable and writable. I think I'm just going to keep going with like the stupidest way to do this code until I figure out a better way. So check read, write, and then check user supervisor. So basically, if so what's the check? Sorry, the music's a little bit distracting right now. So if it's trying, so we're comparing the permissions that are given to us in the function versus the permissions that exist in the page table. And for example, basically if we're trying to write and it's not writable, then trigger a failure. So for example, so if I feel like there's some kind of comparison, like some kind of way, like mask out. Like mask out this specific bit and like compare it to the other bit. And if it's like, I think it's something like if it's less than, this is kind of noob hours, okay, because it's like 0 and 1, right? And so I'm just gonna maybe write out 8. It's kind of silly. It's like some kind of truth table. I mean, it's so really so oops. it's just like user, it's like PTE and user perm. Is it a binary check? So for the writable bit, it's just like, it can be 0 or 1. I'm just gonna, yeah, I don't know. I'm a little bit struggling to kind of get it, so I'm just going to map this out of all the possibilities, just to forward. So here are all the possibilities for the writable bit, at least. And if they're the same thing, it's like, if they're the same thing, then that works. They're both, like, I guess the user perm, it's like, this is just readable. Here is the one where it doesn't work, where the user is trying to be writable. Here's the one where it does work, where the page is writable, but the user didn't ask for that. So basically, here's the only failing case, and that's just like if it's greater. Yeah, if the user perm is greater than the PTE, if the user perm bit is greater than the PTE bit, then that's all there is to it. And I kind of am forgetting where all these macros are. Pagedir, yeah. Right, PTEW, right, there we go. So I think we just need to do something like if PTE and PTEW, no, if user, if perm and PTEW is greater than PTE, PTW. Yeah. Something like this. Right to read only page. Maybe I'm just like smoking crack or something like that, but I think that's how you do it. Maybe I'm, is it not a binary check? Maybe like, but then there's also, there's this exact same thing with the user supervisor thing. Yeah, I'm just gonna kind of stupidly copy this. Yeah. So in the exact same way for the user supervisor bit, it could be 0, which is kernel, and 1 for user. So in the same kind of way, but it's the same principle where bigger like numbers are kind of like, or like, yeah, asking more, or like looser permissions. And so, yeah, you cannot have, it doesn't work if the user requested permission is greater than what is available. That's just simply how it works. So this might be kind of like a very dumb way to do this, but I think this is still correct though. It's PTEU. Like there might be some smarter way to just include that like all together. For example, these two bits are right next to each other. So maybe it's possible to like just get those 2 bits and compare the 2 numbers, but I'm just gonna quickly try to see. Okay. But yeah, so I don't know, this is like kind of crazy. So we could have any, two combinations. Like this is like the PTE and like the user perm, right? Or the, and so user is on the left, read write is on the right. So what are all the combinations? So I'm kind of tempted to write something like, if this thing is just greater than this, it doesn't work, but I'm not sure if that's correct. Because actually maybe, actually wait a sec, maybe. Because in order, yeah, no, I think that actually is the case. Like if the page table entry has like a 1 here, it's not allowed to have like a 1 in the second bit, basically. Like this number is the maximum possible number, because for anything like, yeah, it's not allowed to then have like a 1 there. So if it's a 1 0, then 1 1 would not be permissible, because it's putting a 1, it's like basically trying to do a write when it's only a read. So I actually think simply checking that the user permission is less than or equal to actually works. Okay. Now that I have kind of reasoned through that, I think, very slowly. Yeah. So now I have these basic conditions, and now I just need to, like, technically I could just do goToFails in all of these, and that would kind of work. This is like very bad code. This is like really trash code. I'm just not going to worry about that. Yeah, so if it's greater than movement, if it wasn't present, then that's not going to work. Fail it. And if the permissions, and yeah, if the permissions are greater, I'm just going to put a something like that. So that's mostly it, I think. Okay, I'm gonna kill the palm tree. I think I gotta go. Okay. If there is an error, set this variable to the first erroneous virtual address. So coming back here, where was it? Here. So basically we're bumping along page by page. We don't need to check absolutely every single address because they're all the same within one page. So we can just check page by page, and it's just the first erroneous one is the one to report. And so the most basic way to do this is just set that variable to cur, because we're going in order. So the first one where cur checks it and it doesn't work, that will be the first erroneous address. The only tricky thing is with this rounding that can happen at the beginning. So technically, if we rounded down, so technically if VA pointed out of bounds already, basically, then we kind of need to maybe remember that or something. I don't know. because technically we should be returning VA as the first erroneous address, not cur, but cur is rounded down. And so the worst possible way to code this is like if cur is equal to VA, or if cur is not equal to VA, that means some rounding happened. Wait a second. So on almost every case, we just simply want to return. We just want to set this thing to cur, use memcheck, to the first erroneous virtual address. So this is not correct, but basically this is kind of like the most common case. Equals cur. There's just this like pesky thing of what if we're on the first one? Right? So it will work here. It's just if we're on the first one and it's invalid, we should return VA. Yeah. It's the first one we should return VA. So something like if cur is equal to round, I'm just gonna like, I don't know, down. I'm just going to stupidly recompute this again. So if we're failing and cur is still equal to round down of VA, then return VA. Else. Or otherwise, yeah, this is kind of stupid code. Something like this. Improve this. Or maybe, you know, maybe I could have approached this differently, where it's like, there's actually no real reason to round this one down. I just need to eventually make it aligned. So I could actually start it here, and then just instead of bumping it a page size at a time, I could just bump it to the next page and then continue from there. Yeah, I don't know. I kind of don't want to really spend too much more time on this, so I'm just going to leave it with this kind of bad code. Yo, what's up, Raj? Go-to statement, lifeline of kernel, whereas bad practice in making software. Yeah. I think in a lot of cases, yeah, you shouldn't use go-tos, but I think for error handling, it's actually the best tool for the job in C. Yeah. Working on checking page permissions for addresses that user space tries to access. Yeah. Okay, this is like the worst function in the world, but I think it might work. Does it compile? No. Oh man, all these const things, that's so annoying. I'm just going to, I'm going to remove the const. That is just incredibly annoying for the moment and not that helpful. Oh, comparison between pointer and integer. Wow. Okay. T. Assignment to unit pointer T. Yep, welcome to bad code hour. Okay, and it compiles. So are we really calling this? So we're calling this function basically on every syscall, I think. Or are there actually no callers yet? Okay, change. Okay, I'm going to just wrap this up and then gotta go. Change kernel, syscall, that's, oops, wow, I'm trying to print my terminal. Syscall, that's C. Sanity check system call arguments. So, for example, here, user mem assert, right? And what do you pass? You pass the kernel. For example, I guess this. So now we receive the system call for printing a string, but before we actually do that, we're going to validate the arguments that user space passed us, which I think just looks like that. I think that's currently the only system call that operates on arbitrary pointers and stuff like this. So wish me luck. Buggy hello. Hello. So this is that one, right, that tries to sys puts like this super low number and run. Let's see. Fingers crossed. That's right. Okay. Is anything else? Should not panic. You should see this thing. Okay, let's go. Oh, it didn't compile. Too few arguments. What? Syscall.c. Syscall.c in the kernel. What do you mean? Also, what is current? I hope that's the current environment. Oh, perm. Ah, interesting. I need to pass a perm. And so the perm here is going to be PTEU, probably. PTE. So this is, it's read only. So it's trying to just read from this region. So therefore, it's trying to read, like you, wait a sec. Actually, yeah, wait, what? User space. So this code is running in kernel space, but it's running on behalf of user space trying to access this memory. So I guess that's why we put the PTEU there, I think. Okay. Oh, okay. And user mem check assertion failed for VA1. Free end, nothing more to do. That is exactly what it says here. So I'm going to call that a massive win. And I would love some W's in the chat if you would care to indulge me. So that actually worked. Who knows, like, if all these checks and stuff I wrote, because this is such a simple test case, but at the very least, that worked. And I think what we can just do to end the stream is run buggy hello 2. So this is kind of the same thing, except rather than going and trying to print like and access the lowest memory possible, basically, which is what we see here with these ones, or this is a bit more realistic, where we're actually taking this hello and we're trying to like make the kernel read like way off the end. And I think this should also work. Like hello 2. And this also worked in the sense that the kernel didn't crash. Whew, okay, that was actually pretty difficult. I always find this kind of coding with this like virtual memory programming where it's like you need to like be all super conscious of alignment and stuff like that to be quite difficult. And so we definitely need some more testing of this here. Testing at set for all of these checks. But yeah, like I think this works, but I'm not totally sure still, but yeah. Anyway, let's just see. So that was exercise 9, and we kind of, I'm not going to do this thing at the end with the debug info, I think, 'cause I don't have the stabs stuff working. So I think that's just it for exercise 9. So yeah, thanks a lot for watching. I'm going to bring the stream to an end here. I'll do my typical thing where I promote myself. So feel free to join the Discord if you want to stay in touch, and like, comment, and subscribe. So, and I'll see you guys next time. Have a nice week, and I'll see you later. All right, bye. See you, Ismail.